So we're going to use that cyclic property of the exponential form of complex numbers to find all the cube roots of 1. Now I know many of you are saying, what do you mean? There's only one cube root of 1. Actually, that's not true. Actually, there are 3 cube roots of 1. Let me show you how we know that. Let's write 1 in exponential form. So we know that, first of all, let's think about what it means for something to be the cube root of 1. We're going to say that z is a cube root of 1 if z cubed is equal to 1. That sort of makes sense, right? So you've been taught in the real numbers that there is only one such number that works like that, and it's 1. Well, let's write 1 in exponential form, and then we'll cube it. So first of all, let's write 1 is equal to e to the 0, or I could write it as e to the I in 0 degrees. I know that 0i is the same as 0. I'm just doing it this way to make a point. So let's now verify that e to the I 0 is in fact a cube root of 1. So e to the I 0 raised to the third power is equal to e to the 3i 0, not theta, 0, which is equal to e to the 0, which is 1. So check. E to the I 0 is in fact a cube root of 1. Now let's see if we can find another cube root of 1. How about e to the I 0 plus 2 pi over 3? I know that I could just write that as e to the I 2 pi over 3, but once again, I'm just trying to demonstrate something here. So let's see if this is in fact a cube root of 1. You can probably guess that it is because I wouldn't have put it up if it isn't, but let me just show you why. So e to the I 0 plus 2 pi over 3. We cube that. Recall that when we nest exponents like this, we can just multiply them. So recall that e to the x to the y is equal to e to the xy. So I'm just going to multiply I times 0 plus 2 pi over 3 to the 3. So this is going to be e to the 3i 0 plus 2 pi over 3, and that equals e to the 3 times 2 pi over 3 is 3 times 2 pi over 3 is 2 pi. So this is going to be e to the 2 pi I. Now we know that e to the 2 pi I, from what we saw in the previous example, this is just one trip around the circle from e to the 0. So this is just going to be the same as 1. So e to the 2 pi I equals 1, thereby showing that this is in fact a cube root of 1, because if I cube it, I in fact get 1. Now let's see if there's another cube root. How about 0 plus 4 pi over 3? So once again, let's cube that number. E to the I 0 plus 4 pi over 3 to the 3. That equals e to the 3i 0 plus 4 pi over 3, which equals e to the 4 pi I. And as you can guess, e to the 4 pi I is just 2 trips around the circle from e to the 0i. So once again, that also equals 1. Okay, so let's see where, let me just draw these. E to the 0 is just this number. E to the 0 plus, e to the 2 pi I, so this is e to the 0. This is e to the 2 pi I, is just I go once around and get to the same number. And then e to the 4 pi I start here, I go twice around and get back to the same number. In all 3 cases, I end up right here at the number 1. So all 3 of these are actually cube roots of 1. Now where are they? This is why, and then you're going to see why I've been writing them in this form. Let's draw a set of axes. Okay, so e to the 0 is e to the I 0 is clearly this point here. So this point here is clearly e to the I 0. Now let's look at where e to the I 0 plus 2 pi over 3 is. So that's going to be at the angle 2 pi over 3, which is going to be at a distance of 1. So let's see. That takes us to about there. And 4 pi over 3 takes us about there. I'm not drawing these quite to scale. There we go. I think that's right. Yeah, okay. Just making sure. Yeah, I've got the distances right. Okay, so this is e to the I 2 pi over 3, and this is e to the I 4 pi over 3. Now, take a look at where these all are. They all kind of lie on the same circle. They all have the same radius. Not kind of on the same circle. They all do lie on the same circle. They all have the same radius, and look at how the angles are evenly spaced. Each one is exactly a third of the way around the unit circle. Excuse me. Each one is exactly a third of the way around the unit circle from the other. So this suggests why it is that I've been writing these as 0 plus 2 pi over 3, 0 plus 4 pi over 3, is we start with kind of the obvious cube root of 1, and then we add an angle that takes us a third of the way around the unit circle to get to the other one. We add another angle, we add another third of the units, another third of the circle to get to the third root, and then by the time that we do it again, if we were to add another third of the circle to go from here over to here, we'd just be back to the same root and we'd start repeating ourselves. So even though we could certainly write it as e to the I 0 plus 6 pi over 3, that that itself is not even a different number from 1. So we've just gotten back to the same root. This suggests something about how many roots there are. There are actually, if you ask how many nth roots there are of any number, the answer is that there are n of them, and they're all at the same radius, spaced evenly around the circle. If we're talking about the seventh roots of something, there are 7 of them, and they're each placed at the same radius, 1/7 of the way around a circle from the other ones. So, all right, so we've got now the 3 numbers. I just want to show you what they actually are in Cartesian coordinates. We have e to the I 0, e to the I 2 pi over 3, and e to the I 4 pi over 3. This is, of course, going to be 1. This is negative 1/2 plus root 3 over 2i, and this is negative 1/2 minus root 3 over 2i. How do we know that? Well, we know that e to the I 2 pi over 2, sorry, e to the I 2 pi over 3 is equal to cosine of 2 pi over 3 plus I sine 2 pi over 3. And you can check me, but you'll see that 2 pi over 3, cosine of 2 pi over 3 is negative 1/2, and sine of 2 pi over 3 is root 3 over 2. So that's how we get this first number here, and if we plug in 4 pi over 3, that's going to give us the second number that you see here. So these are, in fact, in rectangular form, the 3 cube roots of 1.